presentation. So if I just, to everybody, thank you for coming. This, I think, is the 5th webinar of a series of webinars we've been doing on climate services. I'm Tracy Irving, the Managing Director of Oasis Hub. So again, thank you very much for coming, and sorry about the difficulties in getting Brendan, who was supposed to host the webinar, on. But I'd like to introduce you to Ralf Toumi, who is a professor at Imperial College London and who's been working with the H2020 insurance project funded by the European Commission. And a part of that, he's been working on new tools for climate innovations. So if it's okay, Ralf, I'll pass over to you.
Thank you. So what I propose to do in this webinar is to just run you through the documents and things we have already uploaded on the Oasis Hub. I'm going to share my screen now. I hope you can all see my screen. Tracy, can you confirm?
Yeah, yes, we can. Yeah.
So in this webinar, there are basically 3 data sets I want to describe to you. One is a catalog, the other one is an event generator, and the third and final thing is what you see here is the typhoon forecast. So to find the catalog, I'm just going to put it in Imperial College, type it properly, of course. And then there's 6 data sets, and then you see this thing. This is the China landfall catalog. So if you open that up, there is a, so if I click the CSV, you can actually see the various numbers. But what I will do now is go through the documentation, but maybe just to go through the catalog. So basically you've got the name of the event, the year, the date, the province. So this might be of interest if it's parametric insurance, longitude, latitude, minimum pressure, maximum wind, Rmax, if we could identify it, various wind radii, integrated kinetic energy, I'll explain that, and then our estimate of the precipitation of that storm as well. So accompanying with that catalog is this document, which I'm just going to upload. So that's for you to read. So what I'll do is I'll just guide you through how this catalog was set up, and then later on, the motivation for this catalog, actually, it's the basis of the event generator, which I will describe in the next step. So the catalog is purely based around landfall. And the specific reason we wanted to do that is that we believe that the current approach of doing the CAT modeling with tracks is I think somewhat misguided. So what we believe is actually important is the last 24 hours of the landfall process. And you could argue that the track might be important for surge and things like that, but it's certainly not important, for example, to monitor genesis, to monitor the track thousands of kilometers over the ocean. So we think it's much more sensible to have an event set that is statistically consistent with specifically the landfall characteristics. So that's our approach, which is different from the normal cyclone modeling approach, and I welcome a discussion around that. So what sort of variables then are we interested in? So I mentioned that before, the storm, the name, various wind radii, the precipitation, and what we call also the volume rate. So this is the rain within 500 kilometer range. So there's a breakdown of the sections. So the various source data we're using. Specifically, we want to talk about how we derive the size of the cyclone, integrated kinetically, and the precipitation. So there's a little thing about parametric. So one of the things, since we're interested in China, we were interested, for example, one of our initial applications was maybe a parametric insurance product. If you were trying to do a parametric product in China, for example, with a customer that might be the province in China or something like that, it is actually one of the choices you have in the Pacific is what data would you use to trigger the insurance. So the insurance would be triggered at, say, some minimum pressure or maximum wind speed. But actually, uniquely in the Pacific, there are 5 agencies that will tell you slightly different numbers about what the minimum pressure was, what the wind speed is, and so forth, and actually even the exact location of the landfall. So widely used data for building CAP models is the US Navy, what's called the Joint Typhoon Warning Center. But I think that would be problematic. I don't think you would be able to have a parametric insurance product in China based on US Navy data. So I think the Chinese Meteorological Agency would be the natural choice. The other reason I think it is a sound choice is that, remember, we are very much specifically focused on landfall. So although there have been intercomparisons of different agencies, and some people argue that the US Navy might be the superior data set, and the Japanese is the WMO provider for that region, they're all very much focused on the open ocean. And actually, when it comes to landfall, many of the techniques, the Japanese, for example, the Dvorak technique doesn't really work at all during the landfall process. It doesn't work very well at all. So during landfall, it's quite a specific set of circumstances, and we believe that the Chinese Meteorological Agency actually has unique access to its own database. So its own database of observed winds and pressure. So we think inherently that there should be a better data set from the Chinese, particularly at landfall. So that's the basis of our model, is the Chinese Meteorological Agency data set. So the other issue is the footprint. This is a major issue for all cases. So the CMA is now beginning to publish radii of maximum wind speed, and we've extracted some of those. And I will show you later on how we actually extrapolate the wind field using our wind field model. And we investigate this issue of integrated kinetic energy. And we have shown that in the Atlantic, we published this. This is actually a better measure of damage than minimum pressure or maximum wind speed at a location, which is not surprising, because if you think about them, we estimate here that the maximum wind speed in a Cat 3 storm, given a radius, typical maximum radius of maybe something might be typical. It's only going to be a few percentage of the area is going to experience the maximum wind. So it's unlikely that the maximum wind is going to be a good measure of the damage. Of course, much of the damage is caused by flooding, as you know, so therefore we need to do something around rainfall. For the source data, we take the IB track, so that's the public data, and then we choose the CMA data set. And here's an example of the time series, the annual frequency of landfalling cyclones in all of China. So there's the entire Chinese coast, and you will see here that we didn't try and produce a trend through that. You could see maybe there's some suspicion about the earlier values might be a bit lower. It's hard to tell, but it's difficult to argue that there is a trend there, so we're not going to do that particular argument. Now, the next thing is we need to work out a probability of where the typhoon will make landfall. And so therefore we need basically what we call a two-dimensional probability distribution, which is the probability of landfall and then its latitude or its location on the land. Some other comments here about the availability of the data. The rainfall data is from the satellite. So for product consistency, we decided not to use the Chinese rainfall data, which actually also is not completely publicly available, but the satellite data is available, and we think it is a useful product for a large-scale volume of rain. It may have its problems for peak rainfall, for example, in the quarter, where the resolution might not be sufficient. So you can see here that the scale is about 25 kilometers 3 hourly. And this is a comparison of the rainfall observed by the trim data set we're using, and some single gauges that was put on buoys. And you can see there is correlation, very good correlation. over the ocean, so that the data set seems to be well behaved. Later on, I'll also show you some damage relationships. So this is to do with maybe building a parametric model, or also simply working out the relationship between damage and the variables. And we took the publicly available EMDAT data, and we aggregate that for province scale. So the first thing is the size. So there are many metrics of size, and we think size is very important. So widely used metrics, things like ACE and Power Dissipation Index, do not include the size. So they have been correlated with damage, but we don't think that's really sufficient. And so to show an example, that even if you simply take our gale force radius, and this is damage in South China, and you get some reasonable correlations, so there's some outliers, it's not a simple relationship, but there is a relationship which explains maybe 40% of the damage as a simple function of where the radius goes in the radius, not quite to the square, to the power maybe 2.6. So there is a relationship between the radius and the damage. So that's important information. So the information about the full radial profile is not available in the abstract. And for the most recent events, only Rmax or R18 are available. So therefore, what we did is we combined it with an analytical model, which is published. So we call it the Imperial College London model, Lang et al. And it's given here. One of the great advantages of this model is that it has no tuning parameter. So it's based on a pure physics derivation. It makes an assumption about the shape of actually the temperature profile inside the core as a Gaussian function, and then through the derivation in this paper, it comes out. So the key point here is that all the variables are reasonably well known. So this is the environmental pressure, the minimum pressure, so this is the pressure deficit. This is the radius at which you calculate the wind speed, and then there's this issue of lambda. Lambda, it turns out, is simply a function of Rmax. So again, something that can be observed. You have R, you have lambda, R, and lambda, and F. So in fact, everything is potentially observable. There's no tuning parameter like in the Holland model. And in fact, we show in this paper here, this model is in fact superior to the Holland model describing the inner wind field without any prior assumptions. So if we have observations of Rmax and minimum pressure, for example, we can derive the entire wind field at all radii within the core. So the area that's the most damaging. And we did here, this is taken from the paper where we compared, so we reconstruct and observe the max using the lambda model in R26. So we take the R26 and predict the max. And so that's the prediction, and then we did it for overland and also just at landfall. And here's the correlation. So the correlation is excellent between the observed Vmax, and that's using our model and taking one wind radii, the 26 meter per second radii. So it's an excellent fit, much better than the Holland model, very low bias. Even at landfall, where we know things are much more complicated, it's a very good fit. So basically, we think this wind model is useful, and it only requires a few observations, maybe one wind radii, the minimum pressure, and you can derive the full radial wind field to be generated. And you just need Vmax or Pmin and Rmax or an R18. So relatively minimal information to reconstruct the wind field, so potentially very powerful. So size data sometimes isn't available. So you might need to do an estimate of Rmax, and so we use this method proposed by Zaf and Zaire, where again they parameterize Rmax in terms of Vmax and in terms of the latitude. So if Rmax isn't reported, then we use this equation, and then we can use this equation to then again derive the full wind field. So we have the full wind field. If you have the full wind field, we can then work out this integrated kinetic energy. And the integrated energy is basically just the sum of the kinetic energies going outwards from the center. So you specify an outer radius, so it could be 200 kilometers, 300 kilometers, you need to decide, or you can decide. And here is a measure of the damage against the integrated kinetic energy, and you can see the correlation is reasonable, an R-squared of 0.5, which I've been told might be sufficient even to do a parametric product. So again, this would be based on damage data in Snapchat. So that's the equation for the integrated kinetic energy. So the integral volume for basically the kinetic energy out to some distance to cover some volume. And you can get a distribution of IKE in the data set. You end up with this type of distribution, and we think that's a reasonably log-logic distribution. So the next thing is the precipitation. And so we want to understand the precipitation. And so therefore we need to understand what sort of data we can use. And first of all, is it important? So again, we looked at the storm damage and the landfall precipitation, and we found, again, a good relationship, a non-linear relationship, because the square of the rainfall volume, so this is within 500 kilometer range. So you have a trim rainfall volume, which is available from 1998. So we can use that observed rainfall volume in the satellite to show that it is useful. So for that, up to after 1998, we have some observed values. But then, of course, we want to build the catalogue, so we need to go back before 1998, and then we simply derive that the rainfall volume itself can be expressed as a linear combination of the maximum wind speed and, again, the radius of the gale force wind. And so the regression is shown here between the rainfall volume predicted against observed and the rainfall volume against the radius observed. So basically, by combining any reported Vmax and reported R18, or indeed reported Rmax, we can then derive the rainfall volume before the satellite era. After the satellite era, we can simply take the observation. So that then this is a distribution of these volume rain rates. So basically now what we've done is basically with that we've created a new catalogue which captures all of the we capture some of the essential properties going back to 1950, the wind field, the rainfall volume. So that's the description. So I'm going to go back to the next thing, which is the event generator. So if you go back to home, you will see there is a facility called Tools and Services. And here you can go into any of them. And I think it's under, it should be under climate change, loss, damage, natural hazards, software, and statistical. Let's just try natural hazards. And it's the first one, very good. So this is an event generator, which is free. So it's downloadable. It's a Python script, so you can download it yourself. And there's a picture here. So there's the event generator, so you can download that. And I will just guide you through the documentation again. So again, what we're trying to do. So we are just generating a landfill generator. So we've got the catalog set up, as I explained previously, going back. And so that forms then the basis of building a statistical model, which is purely based on landfall along the China coast. But we wanted to make it parametric in the sense that we wanted environmental variables to allow us to shift this landfall probability and the intensity. And so we found a variable, which I'll show you, which is the Western North Pacific Geopotential Height anomaly. And I'll explain a little bit about that as well. So the first thing is, how do we define the landfall frequency? So we have a PDF of the landfall frequency, and so just the total count in China. So the total count in any given year actually follows a Poisson distribution reasonably well. So we have a probabilistic distribution of how many landfalls you might get in every 1 year, which seems to be a simple Poisson distribution. However, some of the intra-annual variance in the seasonal total count could be related to sea surface temperature. And actually what we found is not so much the sea surface temperature that's important. I mean, it is, so we could have parameterized it, for example, in terms of El Nino, so there are other ways of doing this. But actually we found that one of the things that seems to be very useful is the covariant, which is the geopotential height in October. So here's the correlation of the geopotential height. So what this is saying is that when the geopotential height at 500 hectopascal is unusually low, then the count is particularly high. So a low geopotential height here favors landfall into the Chinese coast. So we're doing this entire coast. So we find that is actually a better predictor than some of the temperature predictors, for example. So we basically have a predictor if you have a seasonal forecasting model or a climate change model, and you can extract this variable, so the box is here, the geopotential height in there. So you know in any given year if the geopotential height is higher, then you would expect a lower count. If it's lower, you'd expect a higher count. So you can generate a time series with a mean varying depending on the physical condition. You could choose to ignore that and just take a constant climatology, or you can sort of drive the model parametrically, and that's sort of going towards trying to address how you might use this in a climate change scenario. So, and that's the correlation between that. And here's a similar, so there's an example of the number of storms in blue and this height anomaly, and you can see a good correlation between the two. So you can do a regression model count as a function of that. And you can see here different anomalies, and then you put in the number of storms and you get an improved correlation. So there's some of the intra-annual variance can be explained by this variable to 95% confidence. So that allows us the total count across the coastline. But then, of course, we really want to understand also how does that change along the coastline. So we need a generator function for the landfall location. And so we produced a 2D histogram of landfall event location. So this histogram was then smooth with Gaussian kernel to 1/2 degree, and then the smoother goes normalized to 2D probability density function. And then you could randomly sample from this PDF synthetic landfill locations anywhere along the coast. And so figure 5 shows the Chinese national with a catalogue of landfill as its dots in arbitrary colors. So you can see here, so I'm just generating random events. So basically I'm just generating events along the coastline, not the traditional model where I would generate genesis points here and I would move them along here. I'm focusing my probability, I make sure my probability is correct for going along the coastline. So I don't do this gauge normalization, which I know some models do, where they rescale their probabilities to agree with the probabilities that are observed in certain gates or certain regions. So this model naturally comes out of the model. So we think that's a sensible way of doing that. So we have a model then, as in the example I will show you, can actually in the generator you can specify a location. So if you want to specify Hong Kong, for example, you specify Hong Kong, and it will generate typhoon events and give you the wind return period exactly at that location. So there's no need to have lots and lots of tracks or anything like that and hope that somebody across it. It's a continuous function. Probability of a landfall is a continuous function. So we know the landfall position, then we need to work out the intensity. So we need the pressure deficit. And what we actually found that the pressure deficit itself is a function of latitude. So on the whole, cyclones tend to be a bit stronger further south. So therefore, we factor that into our model, that we make the storm slightly stronger in the south, and it roughly follows a log normal. So basically, the pressure deficit is a log normal, and we shift that log normal distribution with latitude. And then we have a relationship between the Vmax and total pressure, and we also show that that's not surprisingly a good relationship, and that sort of agrees with what we have already in the catalogue. So basically, we'll have slightly different intensities at different latitudes because we are accounting for the latitudinal effect of the intensity. And then, like I said, for the catalogue, where the size is not available, we use this Vmax and the latitude position, and then we get the full wind from our lambda model. So from the catalogue, we can take either the observed Vmax or some other wind radii to get, as I explained, the wind profile. And this is the same as before. And similarly for the precipitation, then we have a precipitation model, stochastic model, which itself is a function of the maximum wind speed and again the radius. So I think not many models have this as a function of size, for example. Most models simply do it as a function of intensity. So we recognize that there is a relationship which is just as strong with size as it is with intensity. You can see it here. So I think any rain models that are available, it's obviously not published, so I don't fully know what they do, but my feeling is, and my understanding is that they just model on rainfall volume as a function of intensity, and here we should be a function of radius, and we do that. So therefore, every event has a rainfall which follows this sort of relationship. And then you can generate some results. So there's the catalog of our various events, and then you see the event sets, and the contour is the gale force wind, so some sense of the size, and then we generate synthetically something here which you can see looks very similar to the observed value. And then we generate also, just to check, for example, the frequency of landfall. So the black is the observed, and the grey is the event generator, just lots and lots of ensembles, each of like 70 years length. And so we have the distribution of the maximum wind speed, which agrees with the ensemble. So even the ensemble produces out of history observed events, as it should do. But broadly, it lies in the centre of the line, and the size is a little bit too narrow for my liking, but that's what it is. And the pressure deficit, again, simulate lots of events around the observed catalogue values quite sensibly. And then, like I said, you might want to pick a location. So I think here we picked Hong Kong. And you get the return period for Vmax, so 100-year return value here. That's the wind speed. This is the event generator, so you get a scatter around that. You get the different sizes predicted 100 year, and get the rainfall volume predicted, and so forth. But obviously, it's an event generator, so I could have extrapolated, but I'm just showing 100 years because that's the observed record, and you can see that the simulator captures an ensemble which is sort of in the range of what the event generator is doing. And we could again say, okay, we want to change the 500, the geopotential height parameter, and see what impact it has in Hong Kong, and then we can change the landfall distributions in Hong Kong. It could also change this 500 parameter, like the climate variable. Okay, so that's the catalogue. The last thing I wanted to briefly share with you is the third thing we are tasked to do, which is seasonal forecasting. So this is under development. And what we're showing at the moment is, so it's this forecast, so that's the forecast for this year, 2019. And what we're also doing, so the typhoon count would refer, so what we predicted was that the typhoon count this year is slightly below normal. landfall counts we also do, and then also importantly intensity at landfall. So these are two things that are normally not done, and this is the ACE, which is widely done by European Centre on Earth, which is the Accumulative Cycle Energy in the basin. So these are basin counts, but the middle ones are actually landfill counts, which is our model. So we give, for example, the number of landfills in China in the forecast and intensity at landfill, and so forth. So we have an estimate of that. What we want to achieve is to do this monthly. And importantly, also what we want to achieve. So I explain here what number of typhoons, what we mean by that. So in this case, I am using the JTWC. For the number of landfalls, I am using the Chinese agency because I think they would have a good understanding of what makes landfall in their own country. And again, using the intensity from the CMA. And the ACE from the basin. So for the basin, we use the widely used agency, the WTC, and for the landfill, again, we're using China. So the season forecast at the moment is purely statistical. And if you click here, it should get you to the Imperial College website. So the idea is there we will update so it's last updated 15th of October, so we're just about to do another update. The idea is that we're going to update it every month. We're also going to explain more about the methodology, how we do that. We're going to have a paper on that in the coming year. Ultimately, also what we'd like to do is collect lots of different agencies' forecasts and show them in a transparent way. So some of you may be familiar with the seasonal forecasting hosted by the Barcelona Supercomputer Center. I've been told, unfortunately, that's going to be discontinued, but it's a great model. It actually collects lots and lots of people's forecasts. So that's what we want to achieve. So then people can inform themselves about a consensus rather than taking ours or anybody else. So we're trying to be a sort of an aggregator of forecasts. So far, I've approached 3 or 4 others, and they've all agreed. So I think we'll build up some critical mass, and hopefully over the years we'll get more or less everybody who's interested in that to make the forecast. So we're going to share that openly. And the idea is that we understand that there's no competitive advantage in seasonal forecasting, but if there is a transparent consensus for an active season, that may nudge the entire market one way. Both users and suppliers of insurance could maybe see in a transparent way that there's a risk, similarly as you do. If you see a weather forecast, both everybody, the risk bearers and the risk owners can see what's likely to happen. So we believe a transparent platform is the way to go, rather than customized seasonal forecast to give the insurance sector a competitive advantage. So that's sort of our vision for these seasonal forecasts. So that's ongoing. In fact, all of the things I've said are ongoing, so there will be improvements to all of it. So that completes my my presentation. So I'm open for questions. People have heard me.
Hi, Ralph. I think that Brendan is still not able to get in. He thought he was. But if anybody wants to ask any questions, there's a Q&A box at the bottom of your screen. So if you'd like to ask any questions, please do so.
Do I stop sharing my screen? I guess I'll leave that. No.
So there is a question coming through the chat. How can the generator be used for climate change scenarios?
So we're working on that. So at the moment, as it stands, the geopotential height is a predictor. So you could extract the geopotential height over the West Pacific in the box I showed in the report. So back to the report. The catalog. So I hope people can still see this. So that's what I was trying to say. So the event generator, so the probability of landfall, is controlled by this variable here, the geopotential height at 500 hectopascal. So what you would need to do is you need to get a prediction of what would happen under various climate change scenarios for this variable. And we think this is a better variable than sea surface temperature. Yeah, so that's how you would do it. You would use the event generator, you would feed a projected change of geopotential height. So going my Hong Kong example, so if you say, for example, let's suppose that geopotential height actually increases in these various climate change scenarios, that would assume that Hong Kong has a lower landfall count. And then you could run your return period for wind speed, you could end all of that without knowing that landfall count is lower. I hope that answers the question.
Okay, we have two more questions. Is the precipitation model based on a global collaboration of China-specific data?
The precipitation model is completely based on observed satellite, where there is satellite data. So there's the TRIM data, so there's publicly available rainfall satellite data. So that's up after 1998. It's based on observed satellite rainfall data. Before 1998, we used the equation I showed here, which requires reported values of Vmax and our predicted values of R18 to recalculate the rainfall volume at that time. So none of it uses Chinese data directly, but it uses the wind data.
Okay. We've got a question on landfall. How is it calculated, as there are lots of islands off Fujian and Hong Kong?
So these are crossing the eye crossing the mainland. So it's very strict definition.
Okay.
Maybe the anonymous attendee. Maybe I didn't. I think I maybe misunderstood the question. The question I think is, could you use this method in other parts of the world? And the answer is absolutely. And in fact, the entire method I just explained about the event generator could easily be reproduced anywhere around the globe. I think that's what the question actually refers to. Yeah. So the model I'm showing you is for China, but the concept methodology is completely global.
Okay. We also have another question. How accurate are the seasonal forecasts?
So we are getting, there are different measures of skill. So we're going to publish a paper on this. So the seasonal forecast scale is similar to what the European Centre do at the moment. So there's what we call an enhanced scale of maybe 10 or 20% above climatology. Importantly, though, it's actually, there are not many landfall forecasts, and we think we have a similar scale in landfall as we do for the open basin. So we will publish a paper to explain exactly our methodology and the accuracy. But it's a seasonal forecast, so there are uncertainties.
Okay, so another question. So what's next in the sort of research track for you, Ralf?
So there are a number of things really. We want to, going back to the catalogue, we want to explore other climate predictors than the geopotential height. So I explained geopotential height seems to work, and we are looking at other variables that could also be used for climate change or indeed seasonal forecasting. So that's one aspect. The other aspect, which at the moment what's freely available is the total rainfall volume for the storm. But we also have now another model, and we're thinking of making that maybe proprietary, which actually does the rainfall gridded. So it becomes rainfall as a function of the radius, the storm center. So we're already giving the wind footprint freely because that's calculated from our wind model. So I think the next step would be to do a product of rainfall, which is gridded. So like a 1 kilometer gridded, a 2 kilometer gridded rainfall product. So that's nearly ready, but I think that won't be free on the hub.
So how could people get hold of that if they wanted to?
So I think that's really a question to you. I think it's the way the hub is going to organize it, right? So I guess there'll be a data catalog flag, or sorry, there'll be a free version of the event generator, and then there will be a premium version.
Okay, so it'll be for sale on the hub.
Yes, and then it would be flagged up. And then
okay. Cool. We've got one other question. One of the benefits of the existing track generation is that it allows basin-wide landfall and damage correlation. Would your method be extendable somehow to account for the correlation of China and Japan landfalls to damages?
So, yes. So at the moment, so I should have said this is another aspect of what we're doing. So what I showed you is we are simply predicting the total landfall count in China. So we're taking that as a single Poisson distribution. But actually we now have another version of the model which distinguishes the north and the south of China. So it indeed tries to capture the correlation or lack of correlation between the north and the south. And so our approach for that will be that we will have different predictors. The geopotential height I showed you is for the total count in China, but once you separate it out for north and south, you will have different predictors. And therefore, if you have different predictors, you will account for the correlation between China and Japan or any region that you choose. So you basically would drive a local Poisson model, but with different environmental variables. And to the extent that these environmental variables change year to year, you will create correlations and anti-correlations. So it can be. And in fact, I would argue that's actually more consistent than what's done in the track generation. The track generation randomly distributes it between China and Japan. Doesn't account for the fact that the reason there is correlation or anti-correlation is because there are certain weather states, like I don't know, El Nino or the West Pacific High, and that determines whether or not you have correlation or anti-correlation. So track models should capture that, but they don't. And I think our model will do quite naturally. It can do.
Okay, great. And finally, are you modelling the total accumulated rainfall per event per grid?
So that's what I was trying to say. So at the moment, we're simply the volume integrate. So it's the rainfall volume over 3 hours or 6 hours, sorry, 6 hours at landfall. But it's the integrated over 500 kilometers. So it's not gridded. We will have a gridded product, but that's the premium product I was trying to refer to. So there will be one.
Okay, great. So thanks, Ralf, for talking to us all about quite a lot of work that everybody needs to think about, really, because there are some new methodologies here. Just to sort of finalise the event, all of these things, or most of these things, are already on the Oasis Hub. But we're also gathering other kind of data onto the hub all the time. So please come and look at our data. Also, to be clear that any commercial data on the site is sold at the same value as the provider. So in other words, we're trying to create sort of a global community around data and people that collaborate around data. And this obviously is for the benefit of everybody who's looking for data from across the world. So if you have any data or you're interested in any data, please do get in contact with us through the site. So we have one more webinar coming up in 2 weeks' time, and this is looking at a flood model for the entire Danube region, and how this model has been used for both insurance purposes but also for local kind of adaptation planning. So that one, I believe, is on the I haven't got the date, so I believe it's on the 19th of November. Correct me if I'm wrong, one of the team, but if not, we'll let you know what the actual date is. So thank you all for coming. It's been great to have you, and if you've got any further questions, please do get in contact with us, or we can contact Professor Toumi with any further questions or interests you have in everything we're doing. So once again, thank you very much, Ralf, for your time.
Thank you. Bye.
Okay, bye everybody. Thank you for coming.